It's great to have you here for the first session of our course on counterfactual explanations. I'm particularly excited for today's presentation, which will be given by Amit Sharma, an estimated expert in the field of explainable AI from Microsoft Research. Hi, Amit. Thanks for joining us. I know that it's late for you. And yeah, I think that we can start. I know that you start to share your screen, so yeah, over to you.
Okay, thank you so much for inviting me. So my journey in explanation has come from a slightly different path than most people. So my experience was in causality and causal inference. And when I looked at the explanation literature for machine learning, I thought that perhaps we can use the same kind of causal principles to explain models as well. So I'll talk about that journey and also give you examples of how you can explain machine learning models, not just in tabular data, but also text or images. But before we do that, I want to give you some bit of perspective, especially historical perspective, on why counterfactuals are so impressive when it comes to explanation. In fact, like this has been the major way that people have used to assess human decision making. So I'm showing you one example from a study in Germany where a researcher was interested in a social scientist to study whether employers in Germany are biased against women wearing a hijab. And typically, if you just look at, let's say, job applications and see how many people apply and how many people get a response, it's really hard to figure out whether it was because of someone wearing a hijab. And it turns out, interestingly, I don't know why, but in Germany, you are supposed to add your photo to your resume. And that's why they were able to sort of look at this question. So of course, like if you have two women, one of them is like on the left and the other one is on the right, it's really hard to say whether if there's a difference in job response rate, whether it's because it's a different woman, it's a different qualifications, it's a different name, and so on. But if you just think of a scenario where the same CV is sent, but all you do is you change the name, then you can logically conclude that if there is a difference in response rates, it has to be because of the name. And similarly, you can also imagine in this study, actually, what the researcher did was that they had the same woman either wear a hijab or not. And then they were able to find out whether there was a difference in job response rates if you changed only the hijab, but kept everything else constant in the CV. In this study, unfortunately, they did find that there was a bias. And I'd point you to this study if you want to learn more. But this has been sort of a mainstay of a lot of social science research in how we think about human decision making and how do we make assessments about what might be going on. And why is it so powerful? Because as you can intuitively also imagine, right, what's really happening is that we only change the specific input, but we keep everything else constant. And because you can now reason about everything else relevant being constant, any change that you observe has to be because of the specific input that was varied. And so what I'll do is in today's talk, I'll try to apply the same principle to machine learning models. So now instead of analyzing human decisions, we are going to analyze machine decisions. First, I'll talk about tabular data because the concepts are pretty clear and standard in that field. And so we'll talk about an algorithm and a machine learning library that you can use to explain models, which is called DICE. And then finally, I'll generalize this idea to images and text as well, because really, I think today, a lot of the machine learning interesting examples are happening in text and images. If you have any questions during the talk, feel free to just speak up. I'm happy to take questions at any point of time. Yeah, so don't wait till the end. So just formally speaking, we have the intuition now, but let's also formally define a counterfactual. And so if you have any system and the system produces an output Y, we define a counterfactual as the value of y under a value of x that you can define, keeping everything else in the system the same. In fact, the more formal way of saying it is that it's everything else unaffected by x, because a counterfactual by definition means that if you change x, then it will also change all the other variables that are affected by x, right? So for example, if I change something upstream in some kind of a process, it also reasonably should also change all the downstream variables. And so typically it's a really hard problem. So for example, you might want to estimate the probability of what would y be had x been some other value. And in general, in the real world, I mean, who knows? It's a probability distribution, right? So you do this a lot of times and maybe you can find the distribution. But actually, machine learning is really nice because if you're trying to explain a machine learning model, it's going to be some deterministic model. So we don't really need to estimate the probability. All we need is to just estimate it once, right? So if you just estimate the value of y at different values of x, that's it. Like at each value of y, you'll get that counterfactual. So in some sense, explaining machine learning models is much simpler than explaining the real world. And once you get this basic principle, you can even immediately start thinking about applications which can be far-reaching. So let's say I have some feature small x, sorry, not bold x. So bold x means all the features, and I just change one of them, which is xi. So you can simply compute this quantity, which would be the expected value of y when I change x to x dash, minus the expected value of y under the usual value of xi. And just by comparing these two things, which actually reduces to just comparing the output of the model under these two inputs, you can get some insights. You can think about how important xi is, because if xi is important, then this difference has to be big. If xi is a sensitive feature, for example, race or gender, then you can also think about this as a level of bias in the model. So you can also think of it as a tool that can allow you to detect unfairness. But also more generally, you can also think of it as a debugging tool. So suppose you know some xi variable for which the model should never change its prediction. In that case, you can also think of this as a debugging tool. I see a question in the chat. I'll just go to that. Oh, yeah, that's a good point. Yes. Yeah, so I think we were starting with tabular data. So yeah, so we were starting with tabular data. So I was thinking of these old school classification models where they are really sort of imagine like a neural network, which just gives you one output given an input. But you're right that today there are many other options, so there are generative models as well. And so in that case, yeah, you'll need to actually estimate this probability distribution. So far, I've not worked on them, but that's a very good point. Yeah. Yeah, so I think for this talk, when I'm saying machine learning model, think of it as either the standard machine learning models, like logistic regression, or the deep learning models, which are essentially sort of an architecture of many layers, but then ultimately it just gives you one output at the end, like a CNN. So now you might be thinking that all this is fine. This seems nice, but why would I use counterfactuals when there are so many established methods of machine learning explanation, which are made specifically for machine learning? Well, that's true, actually. So there are well-known methods like LIME or SHAP and many others that came after them, which are really useful to understand which features are the most important for prediction in your model. So typically people produce charts like this on the right, where it tells you feature 1 is the most important, feature 2 is the least important, and so on. But there are many cases we found where feature importance is not good enough. So imagine that you are a decision maker, or maybe you're a person who has applied for a loan from a bank, and your loan gets denied. So obviously you're not happy, and you ask the bank, why did you deny my loan, right? And the bank might say, oh, I use a machine learning model. I don't know. Here's the explanation that I have. And so it will tell you that annual income is the most important feature, credit years is the least important feature. But this is not useful, right? Because this does not tell you what you should do so that you could have got the loan, right? So maybe your annual income needs to be increased 2 times. Would that get you the loan? You have no idea. And so this kind of feedback is not actionable. Whereas counterfactual explanations are of the kind which will give you what if scenarios. So a counterfactual explanation the bank could have given is that I'm using a machine learning model, and you would have got the loan if your annual income had been 100,000. Right? So notice the difference here. The first one, it gives you an overall picture, which is useful in many cases, but it doesn't tell you for individual inputs what to do. Right? And similarly, you can also imagine a decision maker thinking about why should this person not get the loan? They just want to explain the decision the bank made. Even in that case, sort of this kind of plots are not useful. You would actually want instances of the violation that the person did or what was the reason that they could not get the loan. But you can also imagine it in a different way where feature importance based explanations may not be high fidelity. And I think this is a much more stronger limitation of such methods. What I mean by that is you might see that annual income is the highest important feature here, but it may not mean that changing annual income even by some reasonable amount would actually get you the loan. Nobody knows, right? I mean, maybe it's the most important feature, but your annual income is so low that even if you twice it or even if you make it 10 times, you're still not going to pass the bar. And maybe credit years is less important, but perhaps if you change it and you just wait 5 years, that's enough, right? So it's not sort of giving you enough information about the model. Whereas these kinds of explanations are interpretable and they're also high fidelity, meaning that if you see an explanation and if you do exactly what it's saying, then you would change the model's prediction. But of course, you cannot have everything, so there is a catch. The catch is that there are roughly infinitely many possible explanations I can generate, right? So how to generate these explanations so that they are actually useful to the person is the sort of research question here, right? So which example should I choose? Which feature should I choose? And then which value should I choose, right? If it's 100,000, is it the smallest possible change that I should make? Is it the most realistic change that I should make? And so on. So I think that's where the question or the research comes in, counterfactual explanations. Any questions so far? Okay. I think chat is also fine. I can access the chat. So if you're not comfortable speaking up, then just type your question. I can see it in real time. All right. So if you now believe that counterfactuals can be useful, we would want to think of what are the desirable properties for counterfactuals. Well, first, they should be feasible, right? And feasibility is a vague concept, but I think you can make it more precise by thinking of proximity. So it makes sense that if there is a feature vector that you're explaining, let's say this person's profile, financial profile, who did not get the loan, whatever counterfactuals we suggest should be proximal, right? So a bad counterfactual would be you would have got the loan if your income was $1 million, right? I mean, it's true, but it's useless for the person because there are very few people in the world, let's say, who can afford to have that much income. Another thing is user constraints. Often people have some constraints in their life, and so they cannot change sort of most things. And so we want to have an algorithm that can respect any constraints that are put in. Sparsity is another one. We don't want to give counterfactuals which are like changing 5 things at once, because again, then the more it just becomes uninterpretable if I say that you would have got the loan if you had to do these 5 things, you had to change 5 things in your life, right? It doesn't make sense. And then of course there are causal constraints as well. So I can't say things like you would have got the loan if your age was 2 years less. It just doesn't make sense. And so these things might seem very like simple to you, very stupid in a way, but it turns out it's really hard because the machine learning model has no knowledge of these things, right? So if you just try to optimize using an optimizer, you can get all these kinds of silly sort of explanations. And so one part of the challenge here is to how to make sure that things are feasible to the user. But the second thing that's also important is that it should be diverse. Because we don't know what the user would find useful, right? I mean, so the best we can do is to just give them a diverse set of options, which help them understand what the model is really looking for. And I think our overall goal is that whatever explanations we give should be actionable, right? So if you're giving an explanation to an end user, they should know what to do so that the model changes their outcome. If you are a model developer, then by looking at these counterfactual explanations, you should be able to know what the bug in your model is, or where your model has problems, and you should try to fix them. So what we did, I think this is by machine learning standards, old work now. This was in 2020. So a lot of new work has happened after this paper was published. And I would encourage you to check out the sort of multiple counterfactual explanation methods that have come up after what we published. But for today, I'm just going to describe this method because it's super simple. And it just gives you that intuition, the early intuition of like, what is exactly do you need to do? And so what we thought of was that suppose if you had a deep learning model and it is differentiable. So what's the easiest way to get slightly different input examples that would change the outcome of a machine learning model, right? So now we are in completely abstract land, right? So we're just thinking of any machine learning model fx. Suppose it generates an output y. Now I want to know what should I change in x such that the output changes from y to y dash. And for simplicity, think of it as a classification problem. It can also work for regression, but I think classification is easiest to understand because y and y dash just means different classes. So what would you do? I mean, if you're using deep learning, you probably already know gradient descent. And so that's what's our first idea, right? Let's just use gradient descent and just slightly tweak the objective. So our goal now is not to learn f, but our goal now is to learn this ci. Right? So what we can say is that minimize this loss where the y of this new ci that I want to generate should be the y I want. So this should be low, plus the distance of ci should be low from x, where x is the original input. And then also we had a term which was prioritizing diversity. So this is the determinant of a determinant point matrix. And essentially what it ensures is that the CIs that I'm generating are diverse among themselves. So that's sort of the obvious thing that one may do. Like if you have a differentiable model and you have a multiple outputs to generate, we can simply sort of write the loss as what we want, right? So we want it to be the different class, and we also want it to be close to the original input. And this sort of technique actually works reasonably well. So here I'm showing you an example from an adult income dataset. So the first row is the original dataset input, where there was some person there. We have their hours per week, education, occupation, etc. And the model predicts that their income should be less than 50K based on these attributes. You can run this algorithm and find the counterfactuals, which are the features that this person should have had so that the model predicts an income greater than 50K, right? So some of these things would make sense instantly to you, right? That the person should have had in higher education. So higher education would perhaps have made their income more than 50K. So when you look at this, you think, oh, this makes sense. I mean, the model is reasonable. It's kind of giving reasonable answers. But then you look at this marital status, right? So the model is saying that if you are married, somehow that increases your chances of getting a higher income. Now, of course, I mean, if you think about it for a second, maybe it's because people, on average, single people are less in age than married people. So married people are older. As you get older, maybe you have higher income. But then as a machine learning scientist, you'd say this is wrong, right? I mean, these kinds of things should not be happening because this correlation can also reverse, right? So these kinds of counterfactuals can be used to inspect the model and figure out what might be going on. Another way to sort of think of this is you can imagine it's a way to generate edge cases. So you just want to see what's the minimum change in input features to change the model's prediction, right? So if you find that it's only changing sensitive features, then it should not be possible. there's something wrong in your model. If you find that it changes the outcome by only changing hours per week, that's okay, but it should only be increasing hours per week, right? And similarly, if you're changing all features, then tiny changes should not matter. This is similar to adversarial robustness. So in this case, I see a question. Are we predicting income or risks of default? So this is a made up data set. So here we're just predicting income. We are not, this data set does not have risk of default. In the paper that I can share a link to, we also have a data set called German credit data set. In that data set, we predict default on the loan. So yeah, so I think in my original example, which is just a motivating example, we are predicting default on the loan. But in this particular data set, this is not default on the loan.
There is another question, Amit. It seems like we expect a counterfactual to be monotonic in the sense that each feature will be locally correlated with the objective. Is that right?
I don't understand what you mean by monotonic. That is it about sort of only increasing or only decreasing relationships? Can you clarify?
So can you please clarify? Yes.
Okay. Yes. So as I can show in this example, for most cases, we do expect that. So for example, hours per week, higher hours per week, we hope or expect that a machine learning model should then say higher income. But there's no nothing stopping you from thinking of more interesting cases. So one of the interesting cases that we've studied is productivity. So we were looking at the number of emails sent, but in general, you can also think of like how many hours do you work per day, right? So you can hope that as you go from 0 to maybe 10 hours, maybe productivity increases. But after that point, it starts to either plateau or maybe even go down, right? So if you're working like 23 hours per day, then probably you at some point you'll become less productive, right? So I think the framework that I'm describing can also model those kinds of relationships and can also sort of let you debug if that is actually happening or not. But it does assume that as a human debugger, you do know what the right trend is, right? Because all these explanations will give you is some trend. And then you have to sort of reason whether that trend makes sense or not.
Thank you. If there is a follow-up question, right?
Okay. So we had this method and we thought of, well, how would you even evaluate these explanations? And I think this is kind of a not a worst, what's the phrase, right? So it's the one of the worst kept secrets of this literature that there are many methods for explanations, but there are very few papers or techniques to evaluate explanations. And the reason is that if you think about the real goal of any explanation method, that is to make the end user understand the model better, right? But the moment you say understand the model better, people disagree on what exactly that means, right? So to someone like me, it might mean that people are able to do their job better. So whatever their job was, like if it was to build a machine learning model, they're able to do it faster or they're able to debug it faster, right? But then other people, reasonable people also disagree and say that no, that's not the reason. You should be able to understand how the model is doing things. You should be able to understand the internals of what it is doing and sort of get confidence that way. So in general, this is really hard. I think the current literature, if you look at it, has many studies which are done with human input, so human behavioral studies, and they often get mixed outputs. Like sometimes explanations help, sometimes they don't. So I think I just want to. I'm saying all this just to preface that this question itself is really hard as a research question, and so I think what mostly happens is that for different applications, people try out different methods and then use the one that makes sense for them. So in our case, we thought like rather than going into that way of evaluating explanations, which can quickly become really hard, we thought let's just propose some basic metrics. So think of these as like sanity checks, right? So we just want to propose some really basic metrics that any good method should satisfy. And we hope that by doing that, at least we can bring in some amount of sort of basic quantitative metrics that people can evaluate methods on. So here's what we thought about, right? So simple things like validity, proximity, diversity, and sparsity. This is something our counterfactuals should satisfy. And of course, I mean, they would, because that's in our loss function, right? So this is kind of cheating. But then we also thought that should counterfactual explanations help people extrapolate the local decision boundary? So what I mean by that is, suppose you are looking at a machine learning model for the first time, right? And all you get are 10 counterfactual explanations for a particular input. By reading them, can you actually guess what the model is going to do on the next input that you see, right? So the idea was that if counterfactual explanations are really helpful, like they are helping you build a mental model of what the model is really prioritizing. And so then you should be able to predict new inputs as they come. So we compared these to a couple of different methods. And the first few methods that we compared to were based on linear programming and also based on gradient descent, but not looking at diversity and other kinds of proximity attributes. So here we found that DICE, which is our proposed method, was able to sort of get more valid counterfactuals while also having more diversity and more proximity to the inputs. But I think to me, what was more interesting was the result that if you simulate what a person would do by looking at these examples, then we found that by comparing DICE versus LIME, just with about 10 counterfactuals, people are able to understand and get a better accuracy on predicting what the model would do. So I want to clarify here, we didn't actually do a behavioral study. We kind of simulated this. So what we did was we simulated this kind of a rational person who, after looking at a few examples, predicts that the next example that they're going to see has to be some sort of a k-nearest neighbor search over what they have already seen. So I want to clarify that this is still as a kind of an approximation of a real human being. It was quite interesting to see that methods like LIME would be based typically on thousands of samples to create their explanation, whereas we were able to simulate that with only sort of 10 inputs and 10 counterfactuals. Another interesting thing that came out, which is really sort of getting into like what is the real conceptual difference between counterfactuals and featured explanation, is that counterfactuals essentially are interesting because even the low-ranked features from LIME or SHAP may be as powerful in changing the class, right? So it might be a folly to sort of not to ignore the features that are low-ranked by LIME or SHAP. So to make this point, just sort of bear with me with a very toy example. So imagine that your machine learning model was just this. So it was like an indicator function of 0.45x1 plus 0.1x2 greater than or equal to 0.5, right? So it's a really sort of toy example where anytime your function increases beyond 0.5, you output 1, otherwise you output 0, right? So as you can imagine, LIME and SHAP look at the coefficients, right? So 0.45, which is much higher than 0.1. And so they would say that x1 is really important. And that's what you see in this table here. LIME gives x1 as 0.4. SHAP, in fact, gives x1 as 1 and x2 as not important at all, right? But if you look at DICE, which is a counterfactual method, and also Wachter CF, which is also a counterfactual method, they tend to give equal importance to both these features. And the reason is, if you look at this model, x1 by itself is not enough, right? So unless you have x2, you will never be able to cross 0.5 and you will never get your class as 1, right? So if you think counterfactually, these methods would say that both are as important, because as far as changing the value of y is concerned, both are required, and it doesn't really matter what the coefficients are. But if you think in terms of feature explanation, or if you think in terms of sufficiency, you tend to believe that X1 is more important because X1 is kind of contributing more importance. So I'm bringing this example up just to sort of share that explanations are not sort of unique, right? So it depends on what you're looking for. So in your application, if you're looking for this kind of sufficiency of features, like you really want to find the big important features, which mostly are closer to sufficiency in predicting Y, then LIME or SHAP kind of methods might be more useful. But if you're more thinking from a counterfactual world, more like a necessary condition, you want to find out the features that are really like necessary to make the prediction, and without them, the prediction won't happen, then counterfactuals are more useful. But they are counterintuitive, right? So I think that's what I wanted to just show, that if you use counterfactuals, you get almost equal importance, even if the coefficients are very different. So if you want to try these ideas out, we did release a library which is open source. It's called DICE, Diverse Counterfactual Explanations. And so far, I've been really happy with the response that we have got. So it started as a Microsoft project, but now we have folded it as an sort of an independent interpretable organization. And I think people are contributing to it. People are sort of adding new algorithms. So if you're interested, you can sort of play with it and try to see if it works for your application. But I don't think the problem is solved. I think the kinds of questions that are still on people's minds are about sparsity and user constraints. So in DICE, we have some simple ways of addressing this. But I think in general, thinking of how do you optimize for arbitrary user constraints is an open problem. And there's also this sort of a very practical thing of annoying thing, actually, of continuous versus categorical features. So if you have a machine learning model which operates on both, so you also have a continuous feature and a categorical feature, it's really hard to reason about relative differences, right? So ideally, I would want to say that change in age from 26 to 30 is sort of some amount of change in the real world. And then there could be another thing like changing your education from high school to graduate, right? That's just a categorical change. So if you're a human being, you can actually assign weights to that, right? You can say that changing age is maybe this much difficult and changing my education is probably much harder, right? So you can assign weights. But I think in an optimization, there's no way to do that. So we always face this sort of practical problem of how do you weight these things, right? So you can't really say that age is going from 26 to 30, so it's 4 times the change from high school to graduate, right? So what we currently do in the library is we just allow the user to mention these kinds of things. And if they don't, then we use some basic default where all continuous features are scaled from 0 to 1, just like discrete features. But I think this is kind of a hard, tricky question. And I think this is one reason that you might find counterfactual explanations sometimes unintuitive. And so then you have to tune these hardness or sort of relative scale of continuous features to make it work. But I think as we did this work, we realized that most people are not interested. So when we open source this library, most people said that this doesn't work for us because we use sklearn, right? And we use all these sort of non-differentiable models, and your method does not work for them. So we came back to this optimization problem and thought about what we really wanted. And so what we really wanted was these 3 things again, right? Just the desirable outcome, proximity, and diversity. And so can we do it without gradient descent was the next question. And it turns out it becomes simpler in some sense. So if your model is not differentiable, think of something like random forest. You can actually use any optimization technique to sample the points that could be counterfactuals, right? So now imagine like you have this machine learning model. It gives you an input, which is 0. And you want to find out which input will be the key, will have a output as 1, right? Well, the simplest, dumbest thing you can do is just randomly sample. So what you can do is that you have some input point in your space of inputs X. you just create a sphere around it, a hypersphere, and then just sample randomly points which are close to that input. And so as a researcher, this felt like, as I was telling you, it felt like a dumb method. But when we tried it in practice, it works amazingly well. I was surprised how well it works, and embarrassed because we had this all complicated method that I just told you about. So I think that's what we then did in the open source library. We also included random sampling. And in many cases, I think there are two reasons it works, right? So one is it's so fast that you can actually sample like 100,000 random samples in the time it will take for the gradient descent to converge. So even though the gradient descent might be better, like even this random sampling gets you to a nice place anyways. And then we also explore genetic programming. I think this is also a technique that kind of gets you sometimes diverse examples. So if you're interested in sort of more diverse examples, you can also try to think about combining random sampling versus genetic programming. But in general, I think if you're familiar with optimization, you can also think of counterfactual generation as really an abstract optimization problem. And so any tools that you know for sampling you can also bring to bear on this problem. And so here's an example of sklearn and using random method. So just to show you a little bit of the API, so what we say is that you first bring in your model, and you also specify which backend there is. So we support PyTorch and sklearn. And then once you've done that, you can initialize this dice object, which essentially is D, M, and the method. And then finally, you have a method that just lets you generate counterfactuals for the dataset that you gave. So here, for example, I can say that I only want 2 counterfactuals. My desired class is opposite. And for the same dataset, can you show me examples? And so that's what this model does. It again tells you things like maybe education and race matter, right? And so you can play with this a couple of times to kind of try to understand what the model really is doing. As I was talking about it earlier, user constraints are really hard. But I think what we've done in the library is the simplest thing possible, where as a user, you can tell us like what are the reasonable values for features, right? So you can say, for example, age can only be between 20 and 30. You could also say that education has to be either doctorate or professional school and so on. And so you can just give permitted range for different features. And if you do that, then the optimization stays within that range. So I see a question here. Can we combine this with MC? Oh, that's interesting. Yeah, you can. Yeah, you can. You can combine it. You can even use, I mean, a simpler thing would be rejection sampling. But yeah, you can do MC as well. That's yeah, we've not tried it, but I think it would be an interesting direction to try it out, just to estimate that probability distribution. But my sense, okay, I mean, having said that, my personal sense is that you might be bringing a really complicated hammer to solve a very simple problem. But yeah, it's a good idea. So far, let's just switch gears a little bit. So I was talking about very simple data sets, which were tabular. But I think counterfactuals become even more interesting if you go beyond tabular data. And in fact, that was my example to begin with, right? We were thinking of sending resumes with sort of the same person, but a different headscarf. So if it's tabular data, it's very simple. You just change the name, right? So if we had our first case scenario and we just wanted the same person, but a different name, it's very easy. I just change the name, right? But if it's image, what we figured out was that you would need some kind of an encoder generator architecture. So what you would need to do is that, actually, this is dated work. So I think if people are familiar with stable diffusion, you probably don't need all of this. You can just write a good prompt. So you have an image and you just write a better prompt to generate an image with some slightly different features. But regardless, I think in even stable diffusion, if you think about it, all it's doing is that it sort of has one encoder where given an original image and some attributes, it's trying to encode that into a latent representation. And then you have a generator which takes in these attributes and the image and generates another image, right? So when we train this architecture, we train it to generate exactly the same image because that's all we have in our training data. But then at test time, you can start changing these attributes. So in our case, for example, hypothetically speaking, if we were training on this data set, we might have an attribute called headscarf. And so if we change this attribute at test time, then we can also start generating images, which would be same person, but now with a different attribute. So to do that, we use this technique called adversarially learned inference. I won't go into the details, but you can check out this paper. It's essentially kind of implementing the simple architecture that I described to you, which is having an encoder to encode the attributes of an image, and then later on changing those attributes to generate new images. So we did this with a dataset called Celeb, which has celebrities' photos, and it also has some attributes like hair color, skin color, and so on. And so what we tried to do was first reconstruct an image. So these are actually people's images, and then change attributes and see what happens to the generated images that we have. So as you can see on this picture, as you go towards the right, different columns have different attributes of the same person. It's not fully accurate. I mean, as you can imagine, this is also a generative model. But overall, you can get the sense that the same person, for example, here goes from the original hair to black hair and then more blonde hair and so on. And similarly, other people, you can also see their attributes are changing. As I was saying earlier, I think people who are familiar with 2023 machine learning would find these graying images not that impressive. But I think the concept remains the same. You can today use diffusion or other models to also generate these kinds of counterfactuals. But the cool part is that if you can generate these kinds of counterfactuals, now you have a general tool to analyze any image model, right? So imagine that you had some CNN classifier with you, right? And you wanted to know how good it is in terms of, let's say, being accurate for different kinds of skin color or being accurate for different kinds of hair color and so on. So you can actually do that now. You take the same person, you generate multiple images with multiple attributes, and you can feed that to a machine learning model and check whether it still gives you the same accuracy or whether it still gives you equal amount of sort of outputs that you were expecting. And so that's exactly what we did. So the first thing we tried to see was for a CNN that we had trained on this data set. So this data set actually has many issues, some of which are that there was some kind of attractiveness label also in this data set. And apparently, people found out that there was a correlation between attractiveness and pale skin. So this is just how this data set was, right? And so we try to check whether that can come out also from our counterfactual explanation method. So what we tried to do was just compare the counterfactual outputs. So we did fx with a particular feature and compare it with f of x dash. And as you can see, the most important features that came up, one of them was pale skin, right? Heavy makeup, etc. And so this is again sort of, if you see this and you are the person building the CNN model, your face should like immediately, you should be worried, right? And so you should fix this. So here's one example of how it can show you some problems. And then similarly, you can also think of it as a fairness tool, because if you just use the same equation, fx dash minus fx, but sort of massage it into probabilities, then you can also create an expression that can tell you how fair your model is, right? So let's say if you were interested in black hair and pale skin, it can sort of give you a bias term of how preferred this kind of feature is as per your model. And so to summarize, there are these sort of three things that I believe counterfactuals are useful for. So the tabular data is something that is very simple in the sense changing the features is very easy. But I think the hard part there is feasibility. Like, how do you know that age 100 is not feasible, or getting to a PhD is not feasible, right? So I think those kinds of things are hard. We've made some progress with the DICE library, but I feel like there's still a lot more work to be done to make it possible. And so if you want to try it out, you can either use the the interpretable DICE library, or I think it's also available on Azure as a part of the Responsible AI toolkit. The second part, which I did not talk about too much, is language data. So you can also think of counterfactuals in language. In fact, that's one of the most natural ways people think of counterfactuals. So let's say I have a sentence and it says, I'm very happy. Right? And so if you're classifying sentiment, you would say that's positive sentiment, right? If I now change it and say, I was very happy, a reasonable classifier should still say that this is positive sentiment, right? But in some cases, you might find that your classifier may be changing its outcome if it does that. And those are ways in which you can actually find bugs in your model again. So if you're interested in language, I think I have my colleague, Marco Rubiero, who has a library called Checklist, and you can try it out. I think it helps you do these kinds of language counterfactuals. And we also have a library from my lab, which is called Litmus, which also sort of lets you look at different counterfactuals in language. And finally, image data, I think, is also interesting because a lot of the data that we get today is images. And so if you can generate image counterfactuals, here generation is the hardest. But if generation is possible, then I think the sort of inferences you can draw are much more meaningful for image data. And with that, I think I'll conclude. I hope I sort of gave you a picture of how counterfactual explanations are useful, because they can give you both interpretability and fidelity. They're also very easy to implement. But I think that the hardest questions are like, how do you actually generate realistic counterfactuals? And so for images, it means like you want to generate realistically looking images. And for text, it means, text and tabular data, it means you want to generate sort of output that looks plausible given the scenarios. With that, I would, want to just thank my collaborators and open up for any questions if you have. So I see one question from Oren: would putting weight on a feature help to see if explainers suggest more actionable changes? Yes, and that's what we do in DICE. Yeah, so as I was telling you about this sort of problem between continuous and categorical features. So in a sense, you can imagine that it's essentially a weighting problem, right? So you can think about weighting either continuous features or categorical features more, and in general, weighting any feature more as you desire. And that definitely helps in the actionability. Yes. I think the only sort of unsatisfying part of it is, like, suppose you have a data set with 50 features. It means a user has to somehow figure out the right way, 50 weights to input so that they can get good counterfactuals. So I think that's the only sort of bad. From a practical standpoint, it's not as easy.
A question building on this, is there any way that you can think about using counterfactual to figure out additional features that make a difference?
Oh. I think, yes, you can, but I think not with the methods that I described in the talk today. But if you think of counterfactuals in general, I think, yes, we can sort of think about getting access to sort of things that might be missing, right? So one example could be that, in fact, today, I think you can use these large language models. So one of the things that I found most useful is that if you're getting a prediction from a model and you get a counterfactual prediction, you can sort of just give it to ChatGPT or your favorite large language model and sort of ask, like, if this is the scenario, what might be the features that might be missing for this sort of strange prediction? And these models are strangely good at suggesting what features might be missing. So I think, not the methods that I'm describing, but if you took one input and one counterfactual example for that input and sort of put it to these models, you should be able to sort of reason about what might be missing to explain those outputs.
something similar to that. Is there a way to figure out that counterfactual, you create different counterfactual for different parts of the data set? For example, if I get something that the model comes back as a borderline, can I create somehow more factual for areas like this, or data points that are similar to this as opposed to the whole data set?
You mean you want to create inputs closer to existing inputs?
Yes, but the point is that not if the model comes back as borderline, the answer is not obvious, but it's close. Can I somehow focus the counterfactual on this? I'm trying to see how you can improve or debug, in a sense, a model. So things that the model is clear and everything is good are less interesting than where the places where it might be mistaken.
Yes. Yeah. So I think for that, it might depend on each model, but what you can do is sort of write this random walk almost in your space of counterfactuals. So let's say you start with 10 counterfactuals, you get some outputs, and you have some way of determining which ones are problematic. And then you can treat those as inputs and sort of explore the space near them. And then you can keep doing this in an iterative fashion. But I think depending on the logic, you can think of it almost like a random walk. And so you can sort of go towards parts of your input space where your model might be making more errors. So I think it's possible to do, but then you have to like sort of some kind of loop around the basic methods.
The question is, how do I actually figure out which the next iteration? It's kind of a genetic algorithm in a sense, or which data points are better to create better counterfactuals?
Yeah, no, so that I don't know. I think that just depends on each application. Like you have a finance application, health application. So what variables you care about, and I don't have a good answer.
Thank you.
So I think sometimes people use these kinds of uncertainty metrics, like where your model gets more uncertain. So that's sort of one way to approach it. But I think it depends greatly on the application and what you're looking after.
Thank you.
So I see one question which is on diving deep with an example. So I don't think we have time today, but I've just posted a link to a notebook, which is like a getting started notebook for DICE. I think if you go through it, you'll sort of understand how with one data set, how you can get counterfactuals. One more question that I see is doing more meaningful causal inference. Yes, yeah. So I think this talk, I focused only on machine learning explanation. But actually, what I'm really interested in is the real causal inference work. I didn't get time to talk about it, but yeah, I mean, these methods are from causal inference. You can use these exact same methods for understanding interventions as well. In fact, what I'll do is I'll just post a link to another open source library, which uses counterfactuals to do exactly this. You can take a look at that library. So this is like, I think this talk is like baby counterfactuals only for machine learning models, but I'm more interested in like the real counterfactual questions, and that's in this do by library. So you can take a look.
Hello, Amit. This is Sari.
Hi.
Am I audible? Amit. Yeah, hi. Actually, I have a very basic question. Like I've seen the examples where you have talked about the text table examples, tabular data. Okay, but when we consider the text data, whether it's a text classification, then how does it perform in terms of counterfactual? Because if I consider the tabular data, I can see those features as a different columns, but when it comes to text, I can see each word is a feature. Okay, then they have weights. And second question is like about how it differs from ML models, and if we consider the deep learning models. And do we have examples in the DICE tutorial, something like that?
So We haven't done much work on natural language, which is why I was pointing you to Marco's repository checklist, where they have done these counterfactuals. But I think in general, I agree with you that natural language counterfactuals are much harder than tabular data. But with the pace of machine learning, I think today that's no longer true. So you could use large language models or even sort of BERT-like models to very easily generate plausible counterfactuals, where you could say that here is some sentence, like Amit is very happy today. Just change the tense of this sentence without changing anything else, or just change the sentiment. Today, there are models available that can easily do it for you. So how I would think of it is, we don't support it yet. I think I haven't worked on that. But if you had an external tool that can generate these counterfactuals, then you can again use these principles on language as well.
Okay, sure. Thank you.
Yeah, there's a question on sparseness. I think, Oren, that just meant that we want to give single feature or at most two features that could be changed. So sparseness is the number of features that change in a counterfactual example. You don't want outputs which say that, oh, your class would have changed if 10 features changed by 0.01. That's just not useful to humans. So that's what sparsity means.
Okay, great. I think that, yeah, we have no more questions. Great. Thank you so much, Amit, for a thought-provoking and insightful discussion. It was great to have you here today. And yeah, I will just also take this opportunity to mention that the next meeting we have next week. Sorry, we have the last meeting of the course that will be held in Microsoft offices. And yeah, thank you again for joining us, and thank you again, Amit. Have a nice evening.
Yeah, it was a pleasure.
Thank you.